Okay, so today we want to study the following system of linear differential equation. This system has variables x1 and x2 and two parameters a and b. Okay, the motivation for this study is to understand how to pass in the system parameters into the ODE solver. Okay, this is important because by the time we start designing controllers for our dynamical systems, we need to understand how to pass in the control signal into the ODE solver. Okay, it is necessary for you to pass in the control signal into the ODE solver so that the dynamical system can follow a reference trajectory. Okay, also in an adaptive control design, the system would have unknown parameters. So it is essential that these unknown parameters be passed into the ODE solver so that our adaptation mechanism can estimate what the unknown parameters are. Okay, so this system, we have given the initial condition 0.1 and negative 0.5 for x1 and x2 respectively. Okay, and the parameter a and b have the values -1. Another thing I want to point out in this exercise is how to define the ODE function in a more optimized manner. Okay, so instead of having the ODE function written as two separate equations in the ODE fund definition, I'm going to cast this ODE system into a matrix equation. Okay, this matrix equation right here. If you perform this matrix multiplication, you would realize that this is equivalent to this. Okay, so having defined the system as a matrix equation, I can make this definition x1, x2 transpose and store it into the vector x, and then the 2 by 2 matrix, I store it in the parameter a. Okay, therefore, I can define the system as this matrix differential equation. Okay, so without wasting any time, let's go into MATLAB to see how to implement this system. Okay, so I define my solver function as ODE. So, okay, I'm going to pass in the parameter a and b. Okay, the next thing I want to do right now is to define the ODE function. Okay, so my ODE function, ODE fun. Okay, so the first thing I'm going to do is to define the matrix A. Okay, so the parameter for the matrix will be coming in from here. First of all, I'm going to use a placeholder, okay, for the time slot. This is because the system is an autonomous system. Okay, the system doesn't have explicit dependence on time. Okay, it has only implicit dependence on time. So such a system is called an autonomous system. So since we don't have time explicitly on the right-hand side of the ODE system, so I don't have to use time in the definition of the ODE system. So I use a placeholder for time. Okay, and then I have the x vector, and then I have the parameter A, and I also have the parameter B. Okay, so now I can define my matrix as this. So the first thing I have the A, then I have 1, okay, then I have 1, and then I have B, okay. Then I can define the x dt equals A times x, okay. Now I have to pass out the x dt for the ODE fund. The next thing I want to do is to solve the system, okay. So I call the ODE solver, in this case ODE 45, which is based on the Runge-Kutta 4-5 method. So I pass in the function, okay? So in MATLAB, whenever you want to pass in parameters to the ODE function, you necessarily would have this @ symbol. Then you have t, s, or t, x, okay? Then you say ODE fun, okay? This function right here, we call it right here. And then t, x, which is the variables of the ODE, okay? So after you pass in the variables of the ODE, these are variables of the ODE. So anything that follow will be the parameters of the system. In this case, we have a, b, okay? Now, the next thing I want to do is to pass in the time span. I want to integrate from 0 to 8, okay? And then the next thing I want to do is to pass in the initial conditions of the system, which are -0.1 and -0.5, okay? Now, this is actually all there is to this system, okay? So I can pass out the solution, okay, x, by writing x right here. Okay, now let's save this system quickly. So if I call this system in the command window, passing in the parameter -1 for A and -1 for B, So I can see that my solution X is a struct. I'm interested in the X and Y data, okay? So I access the X and Y data. I'm simply going to say X, the variable, dot this X right here. And to access Y, I'm going to say X dot Y. Keep in mind that X is actually the time variable, or the time data, okay? The time data, that's the right word. And Y is the X1 and X2 as we saw in our ODE definition. So I'm going to say T equals X dot X and X1 equals X dot Y, but now I want to access the first row. So I'm going to say 1 comma column, then X2 equals X dot Y, 2 comma column, okay, the second row. Okay, now I would like to plot this. Okay, now this time around I would like to use the line command to plot. I would like to use the line command to do the plot, okay, because line command is actually more optimized than the plot function for making graphs. Okay, so I have line T comma X1, okay, and next I'm going to have line T comma X2. Okay, so for this second line, let me give it a color of black, okay, K for black. And also let me define the line style as dash dot line, okay, dash dot line. Okay, now let's run this function again in the command window. Okay, run the function again in the command window. So here we go. So this is the solution of the system. So if you look at this solution, you find out that the solution is not so fine in the sense that the solution points, have a very wide step. Okay, so if we want a more accurate solution, we can actually reduce the error of the system, like the relative tolerance error. And to do that, we're going to define this optional parameters for the ODE45 solver called ODE set. Okay, so in ODE set, we're going to define the relative tolerance, rel tol. So we define relative tolerance to be 10 to the negative 6. Okay, and we can also define the absolute tolerance to be 10 to the, 10 to the negative 9. Okay, now we can now pass in this optional argument into the ODE45 solver. So when we do that and call the function again, so now you can see that we have a much finer output, okay? Okay, so keep in mind that the key takeaway here is how to pass in parameters into the ODE solver. So for the ODE45 in MATLAB, you see, it must be preceded by the @ symbol. Then in bracket, you have the T and X, which are the variables of the ODE system. Then here is the name of the function, the ODE function. Then you have the T and X variables of the ODE system. Then every other thing that follows will be the parameters of the system that you are passing into the ODE function. Okay? Okay, so thank you for participating in this exercise. I would encourage you to like, share, and subscribe because more exciting videos are coming. Okay, so thank you and see you on the next one.